In this chapter, we will have a little bit review of function and their graphs. This will make preparation for the next coming chapters, so that limit, derivative, integration, and all that fun stuff of calculus. But before we get to that, let's have a little bit of review. Review the function. A function f from a set D to a set Y is a rule that assigns a unique value f of x in Y to each x in D. Okay? So the saying that each of the value x will be mapped to a value y, and that value y is f of x. The set D is called the domain, and the set Y is called the range. Example, below we have some basic function in the graph. Let's state the domain and range for each function. Okay. Here the domain. The domain for a linear function is all real number. So from negative infinity to positive infinity, whereas the range is the same, negative infinity to positive infinity. So they're saying that for all the value of x in this function, you can always find a value of y that will match with that value of x. Now the next case, you have a quadratic function. Quadratic function is a square function. You would take any value of x, but because we square it, the answer will be always positive. So the domain here is all real number, but the range is from 0 to infinity. Note that it includes 0. The cubic function, the domain is negative infinity to infinity. The range is negative infinity to infinity. The absolute value, it turns everything to a positive number, right? So the domain is from negative infinity to positive infinity. The range is from 0 to infinity. Next, we have reciprocal function. This is f of x equal 1 divided by x. Well, when we divide by something, we don't want the denominator being 0. So the domain is anything but 0. So you can write that in interval notation, negative infinity to 0, union with 0 to positive infinity. Or the range, and the range, well, the range, since it gets f of x equal 1 over x, the only time, would this function be 0 at any time? No, we can't, right? Because the numerator is not 0, and the denominator cannot be 0 at all. So then the range here is same as the domain. And it with an exponential function, e to the x. X can be of any number. Remember, when we take an exponent, we get close to 0 if x is a fraction that is between 0 and 1. So then the domain here is all real number, whereas the range is from 0 to infinity. Note that we're not including 0. For logarithmic function, logarithm is inverse of exponential, so the domain of logarithm is the range. The domain of logarithm is the range of the exponential, and the range is the domain of exponential. Square root, well, when we take the square root of the number have to be positive, so x is greater than 0. So the domain here is from 0 included to infinity. The range is from 0 to infinity. The domain for a psi function, so from negative infinity to infinity, the range is go from negative 1 to 1. Same with cosine. And tangent. Note that you remember the domain of tangent. Tangent is undefined at pi over 2, right? So tangent have the domain is anything except everywhere that is pi over 2. So you can say that is this x, so that x is not pi over 2 plus 2 pi n. Okay, and where n is real number, n is an integer. And the range is go from negative infinity to infinity. Given a function f of x equals 3x squared plus 5x minus 2, we want to evaluate the function at x equal 2 and at x equal a plus 8. So, first part at x equal 2. Then f of 2 is equal 3 times 2 squared plus 5 times 2 minus 2. That is 12 plus 10 minus 2, that is 20. And we want to see what happened at x equal a plus 8. F of a plus 8 equal 3 times a plus 8 squared plus 5 times a plus 8 minus 2. We want to expand a plus 8 squared and simplify. So we get combine like term. Do we have like term anywhere here? No, we don't, right? So that is what we get. Let's find the domain and rank of the following function. Well, f of x equal x plus 2 to the exponent 3 over 2 plus 1. To do this, first we need to rewrite this in rational and see what happened. So the exponent 3 over 2 would mean we have that square root of x plus 2 together to the third plus 1. Now, in order to take a square root, we need x plus 2 have to be greater than or equal to 0. So to start with the domain, first we need to know that x plus 2 have to be greater than or equal to 0. This means x have to be greater than or equal to negative 2. So that is our domain. So the domain from negative 2 to infinity. Now the smallest value, that x plus 2, the smallest value of this part right here, square root of x plus 2, the smallest of that value will be 0. Take it to the third, that still make 0, right? So the rank is start at 0 and go up. So the rank start at, this is the smallest value equals 0. So then plus as 1. So f of x is smallest at f of x equal 1. So that is 1 to infinity. Well, x plus 2 here cannot be 0. So x cannot be negative 2. So the domain here is going from negative infinity to negative 2, union with negative 2 to infinity. And the rank for this function is go from negative infinity to 0, union with 0 to positive infinity. This is a quadratic equation, so the domain will be all real number. The rank is going to be 5 to infinity. One way of looking at this is here f of x has a positive coefficient. And here, this one is positive coefficient. So f of x open up. This is the vertical shift. So it open up starting at 5. Okay, compared to your parent graph of f of x equal to x squared. Let f be a function defined on an interval I, and let x1 and x2 be two distinct points in I. If f of x2 greater than f of x1, whenever f of x1 less than whenever x1 less than x2, then f is said to be increasing on I. So let's make this sketch. Here we have x1, and we want x1 to be less than x2. And f of x2 is greater than f of x1, so f of x1, f of x2. So the 2 points that we're looking at here would create this sketch. Okay, it's not exactly the best sketch here, right? So as you can see here, we have an increasing function. Whereas if x1 is less than x2, if x1 less than x2, and f of x2 is less than f of x1, so x1 here, x2 here, and we have something look like this. So here we have a decreasing function. Decreasing in the interval I. And that interval is x1, x2, and this is increasing. Okay. Sketch the graph of the following function, then state the interval of increasing and decreasing of the following function. F of x equal 3x minus 2. This is a linear function. Even before we sketch this, we can tell this is a increasing function on all intervals because this have the slope is positive. Slope is 3. And the y-intercept at the point of 0, -2. Okay, so the y-intercept 0, -2. And it increased by, the slope is 3, so it's go up 3 units over 1. Go up 3 units over 1. 3 units over 1. Now we can connect this line. And we try to make it as accurate as possible. And here we can see we have an increasing function. On its domain. Okay. X squared plus 1. So this function here, x squared plus 1, by transformation we can see that this function is shifting up 1 unit compared to the graph of f of x equal x squared. Okay. So we take the graph of f of x equal x squared and we move it up 1 unit. And based on that, we sketch the graph. And this is a parabola. And this point here is 0, 1. So the function here increasing in the interval of 1 to infinity, decreasing from negative infinity to 1. F of x equals square root of x plus 2 minus 1. So this shift down 1 unit. And left 1 unit. Compared to the graph of f of x equal to square root of x. So based on the shape of f of x equals square root of x, we can sketch the graph of square root of x plus 2 minus 1. So we shift it down 1 unit and to the left 1. So this graph starts at the point negative 1, negative 1. And it is going this way. And this is an increasing graph, increasing on its domain. Next, we have a piecewise function. So when x is less than 0, we have the line that is a negative x. So at the origin 0, we have a open dot, and we have this line goes this direction. Okay. And then we have x squared from 0 to 1. So it is a very tiny curve, kind of like this. And we have 1 when x is greater than 1. And then we have 1. So then we have this line. Okay. So the domain of this is already... Well, we're talking about the domain? Nope, we're talking about the interval of increasing and decreasing. So we can see that this graph is increasing from negative infinity to 0, union with 0 to 1. Or you can say that this is increasing from negative infinity to 1. Yeah, and then no change at when x is greater than 1. A function f of x is an even function if and only if f of negative x equal f of x. It is odd if and only if f of x equal negative to f of x. For every x in the function domain. If the function is odd, then the graph is symmetric with respect to the origin, or you remember the graph of cosine of x. If f of x is an even function, then it's symmetric with respect to the y-axis. Now let's determine whether the function is even or odd or neither. Well, I can do that by testing out what happens if I replace f of x. If I replace x by negative x. F of negative x equal negative x squared plus 1. This then equal x squared plus 1. We got back to f of x. So this is even. F of negative x equals sine of negative 2x. Well, sine of 2x is equal to, let's do a little bit trigonometry here first. Sine of 2x is equal to 2 sine x cosine x. So when I replace it with negative x, I'm looking at 2 times sine of negative x times cosine of negative x. I know that sine of negative x equal negative sine of x. So this equals negative 2 times sine of x times cosine of x. That equals negative sine of 2x. And that is the same as negative of f of x. So this function here is odd. F of x, f negative x is equal to negative x squared plus negative x. That equals x squared minus x. It's neither f of x or negative f of x. So this is neither even nor odd. Right? We have the function operation as well. So let's say if we want to find the domain and range of the domain of f of x and g of x, and then we will find and then we do the operation and we state the domain and range of the resulting function. Okay, f of x here have the domain of all real number. And the range is from negative infinity to infinity. For g of x, the domain is all real number that is not negative 1. So negative 0 to negative 1 union negative 1 to infinity. And the range is from negative infinity to 0 union with 0 to infinity. F plus g is equal to x minus 1 plus 1 over x plus 1. You can go ahead and perform this operation and you should get x squared divided by x plus 1. The domain of this function is from negative infinity to negative 1 union with negative 1 to infinity. The range here is from negative infinity to 0 union with 0 to infinity. F minus g, you can go ahead and perform the operation. This we get x squared minus 2 over x plus 1. The domain of this is the same as the domain of f of x. Excuse me, the same as the domain as f of x plus g of x. Let's take a look at f times g, or f times g of x. This becomes x minus 1 divided by x plus 1. Okay. The domain and range is the same. Let's take a look at f divided by g. F divided by g is equal to x squared minus 1. However, remember when we divide something here, g of x cannot be equal to 0. Again, this function ain't going to be equal to 0 because the range here is not equal to 0, right? That's the shape of the graph. So then, the domain and range here is the same as this. Let's take a look at f composite g. F of g of x. then it's equal to 1 over x plus 1 minus 1. This function becomes 1 minus x minus 1 divided by x plus 1. That is negative x over x plus 1. The domain is from negative infinity to negative 1, union negative 1 to infinity. The range here is from negative infinity to negative 1, union negative 1 to infinity. Let's take a look at an application problem. For your law, the volume V of a gas at constant temperature is increased whenever the pressure P decreases, so that V and P are inversely proportional. So when we're talking about inversely proportional, we take in so that V, so it would mean V equal K times 1 divided by P. If P equal to 14.7 pound in inches squared, then V equal 1000 inches cubed. Then what is V when P equal 23.4 pound per inches squared? Well, we have our formula. The first thing we need to do is to solve for K. Well, then K in this case is equal V times P. When V equal 1000, P equal 14.7, so that is 14,700. That is our K. Now that we have K, we can rewrite our formula as V equal 14,700 divided by P. Now we can solve this problem. What is V when P equal 23.4? Well, then that's equal to V equal 14,700 divided by 23.4, and that is 628.2 inches cubed. A box with an open top is to be constructed from a rectangular piece of cardboard with dimension of 14 inches by 22 inches. Cut out the square, each square of side X at the corner. Then you fold it up the side as in the figure. Express the volume V of the box as the function of X. Function V of the box. Here we have the box. The height of this box is X. The width of this box is what? 14 minus 2x. And the length of this box is 22 minus 2x. The volume of the box is equal to x times 14 minus 2x times 22 minus 2x, and now we just leave it as is. $300 books sell for $40 each, result in a revenue of 300 times 40 equal 12,000. For each $5 increase in the price, 25 fewer books are sold. Write the revenue function R as the function of the number x of $5 increase. Okay. So let x be the number of $5 increase. Okay. So the revenue is equal to what? 40 and plus $5 increase each. Now because each $5 increase, we decrease 25 25 fewer books are sold. Start with 300 minus 25 for every $5 increase. This is the function for the revenue. And that concludes our 1.1.